Hi everyone, my name is Z and I'm from University of Michigan. The project I'm going to present today is path-sensitive signatures for control flow error detection. It is a low overhead but high fault coverage software technique to detect control flow errors caused by transient faults. Transient fault is a temporary bit flip caused by environmental effects such as electromagnetic interference, power fluctuations, and high energy particle strikes. With advancement of semiconductor technology, transistor size has reduced exponentially. In addition, aggressive voltage scaling as well as noise margin reduction have also emerged as effective methods to improve the energy efficiency of microprocessors. However, this combination of techniques substantially weakens the architectural reliability, causing transient faults to happen more easily and frequently than ever before. The Oracle's neuron beam experiment also demonstrated that the transient fault rate has increased 13.4 times over the past decades, and the situation will become even worse as the transistor size keeps shrinking. As a result, we need to provide transient fault protection schemes on both current and future systems. We focus on software-based solutions for transient fault detection because it is more attractive for commodity embedded systems. This is high flexibility and free of production cost. These techniques are generally classified into two categories, data flow protection and control flow protection. The former uses instruction duplication to make sure each data used in computation is correct, and the latter relies on signatures to validate the control flows in a program. Although data flow errors are more likely to happen because of the larger area size, they also have higher masking rate. Control flow errors, on the other hand, are less likely to happen compared to data flow errors, but they are much more difficult to be masked during the program execution, as shown in this graph. Therefore, we choose to focus on the control flow protection in this work. A control flow error happens if there is an illegal jump from a source-based block to a destination-based block. A basic block is just a group of instructions with no branch in the middle. Some examples are shown in the right graph with the right dashed arrows. Note that if an error happens in a branch condition, which will cause legal but incorrect control flow transfers, we assume this type of error is covered by data flow protections and therefore not considered in this work. A typical way to detect control flow errors is to use signatures, which is a statically determined value for each basic block in the program. Two steps are involved in this method. Signature update will assign a runtime variable with the signature value of the executing basic block. And signature check will verify the runtime signature to make sure it is from the legal predecessor. A simple example is shown in the right figure. Traditional techniques insert extra signature update and check instructions in every basic block of a program to make sure each control flow arrives at the correct target. Although this detailed checking method has high fault coverage, instrumented instructions also result substantial performance overhead, like 65% in the CFCSS technique. Through the study, we realized that signature update instructions are simple ALU operations, so their effects can be easily hidden by the instruction level parallelism. However, signature check instructions consist of a branch followed by a compare instruction, which are the primary source of overheads. To reduce the runtime overhead, recent works such as ACS propose to use fewer check instructions, but they all lose the fault coverage to different extent. As a result, we aim to provide a new validation method that can minimize the performance overhead while keeping the fault coverage unaffected. To do this, we need to be very careful to reduce the checking frequency in a way so that we can still identify the erroneous control flow paths among the correct ones. To achieve this goal, we propose path-sensitive signatures, or PAS in short. PAS groups basic blocks in a program into large intervals that hold certain properties, such as single entry and multiple exit, and a single loop. Instead of validating every branch instructions, paths will keep updating the signature to record a short control flow history when control flow transfers within an interval. When the control flow across two different intervals, we will check this history with some statically determined value to make sure no error is happened in the previous interval. In this way, we can significantly reduce the checking frequency and improve the performance. With an application divided into intervals, control flow errors can be naturally classified into intra-interval errors, where the error happened in the same interval, and the inter-interval errors, where the error is illegally jumped between two different intervals. To detect intra-interval errors, paths assigns a unique non-negative integer to each basic block in the interval, known as the step value, or SV, showing on the left side of the basic block. Then, paths calculates the cumulative sum for each base block, which is computed by taking the maximum sum of all SVs from the interval entry block to current block along the control flow edge. Results are shown on the right side of each basic block in the figure. To update the signature, paths inserts the update instruction at the beginning of each basic block, which will increment the signature by corresponding BB's SV. Finally, signature checking instructions are inserted when the control flow leaves the current interval to verify the signature matches with the CS value of the corresponding exit block. To maximize the coverage, we keep incrementing the SV of the exit block to make sure that each interval exit block has a different CS value, because making each path sum unique can significantly reduce the probability that an invalid control flow path will produce a valid control flow signature. If illegal control flows happen within the interval, shown in red dashed arrows, the signature will accumulate incorrectly, so the checking instruction will eventually detect this mismatch. If there are multiple paths exist between two basic blocks, we will insert extra increment along the shorter path to make sure the correct signature value is generated. The value of the extra increment is the difference between the maximum path sum and the shorter sum, which is marked in the red square in the figure. In addition, if an interval contains a loop, the signature will get reinitialized every time the loop branches back to the entry node. As a result, we need to insert one extra signature check in the latch block of the loop to make sure no error happens in the every loop iteration, which is illustrated in the BB4 of the right graph. To detect inter-interval errors, paths assigns a unique value to each interval in a program known as the region value, or RV in short, which is very similar to the previous SV value assigned to each basic block. Whenever control flow enters a new interval, the control flow signature will be compared with the interval's predecessor's RV to make sure the branches come from one of the legal predecessors. After passing the checking instruction, the current interval's RV gets updated to the signature. If a branch arrives at an interval but from somewhere else other than its legal predecessor, or the control flows erroneously jump to the middle of an interval, the signature will not be correctly set, so the checking instruction will detect these errors. If an interval has multiple predecessors, we will use an extra signature update instruction to simplify the checking process, showing in the right figure. With the help of the region difference, which is defined in the bottom of the slides, no matter which predecessor the control flow comes from, the signature will always equal to the first predecessor's RV when it reaches the destination. Consequently, a single checking instruction is enough to catch all inter-interval errors. Since both intra-interval and inter-interval error detection use the signature, we can perfectly combine these two checking methods together. To do this, we separate the control flow signature into two parts. The upper half is used for the inter-interval checking, and the lower half is used to detect intra-interval errors. because updating the signature with step values will only change the lower bits, so it has no effect on inter-interval checking. Overall, the expected value at the checking instruction is equal to the region value left shifted by 16 bits plus the CS value of the corresponding block, assuming we are using a 32-bit integer as the signature. The integrated solution is shown on the right graph. Another type of control flow is the inter-procedural transfers, such as calls and returns. Here, works either do not provide a solution or spend too much cost to protect them. To optimize this limitation, we propose a lightweight technique to detect errors that occur when control flow transfer between the calling and the callee side. To protect transfers from the caller to the callee, PASS assigns a unique ID to every function in the program and update a separate function signature with the ID of the target function just before the call instruction. Once arrive a new function, a function signature is firstly checked to make sure the control flow enters the correct target. To protect transfers returning from the callee to caller, two instructions are inserted around the call instruction on the caller side. Before the call instruction, the original control flow signature will be incremented by a random value, and after the call instruction, the signature will be decremented by the same number to restore the original value. If a control flow returns to a wrong location, the signature will not be restored correctly, so the error will be detected at the next signature check. To evaluate PASS, we implemented it as a compiler optimization pass in LLVM. The program is firstly compiled with all three options to perform those standard optimizations and generate intervals. Then PASS will insert signature updating and checking instructions, which will be executed at the runtime to detect illegal control flows. We use Spec CPU 2006 as our benchmarks, including both the integer and the floating point suite. To simulate a control flow error, we perform statistical fault injection experiments in Gen5 simulator. During the simulation, we randomly select a control flow and flip a random bit in its target address to guarantee that every injected fault can result in a control flow error. In addition, we also implement two previously proposed techniques as our baseline. As we mentioned earlier, CFCSS is a conservative checking method that has both high coverage and high overhead, whereas ACS is a more recent work that tries to minimize the overhead by losing some coverage. Firstly, we measure the fault coverage capability for each technique. We inject 1,000 errors per benchmark per technique, and the result is summarized in this chart. Like previous studies, we define the fault coverage of a technique to be the percentage of faults that do not result in solid data corruptions, or SDCs in short. From the result, both CFCSS and PASS achieves around 99% coverage, but ACS only has 96.4% coverage. According to our analysis, missing inter-interval error detection is one of the primary reasons resulting in ACS low coverage. In addition, it will also mean some faults happen inside of loops and large intervals, as its lazy check approach cause some aliasing problems. But PASS can still offer the same level of the fault coverage as previously proposed conservative solutions. Next, we will show the performance overhead of each technique. All results are normalized to the original unmodified program. The light blue color indicates the overhead for intra-procedural protection, and the dark blue color means the overhead for the inter-procedural protection. Note that CFCSS technique by design cannot cover inter-procedural transfers, so all of this overhead comes from the intra-procedural protection. As we can see, the geomean performance overhead for CFCSS and PASS technique are 64.7% and 19.1%. This result shows that PASS achieves roughly 3.4 times less performance overhead than the CFCSS technique. Compared to ACS, PASS shows a slightly better performance improvement, which is about 2.4%, resulting from the high efficiency in the inter-procedural protection. But PAS is a lot more effective since it keeps the same level of fault coverage as those conservative checking solutions. Lastly, we also measure the detection latency for each method because a longer detection latency generally increases the overhead for the potential recovery schemes. However, we do expect PAS to have a higher detection latency since it reduces the validation frequency to the interval granularity. Results are summarized in this figure. Within 2K, 5K, and 10K represents whether the detected error is reported within 2K, 5K, and 10K cycles after the fault injection. Although PAS experiences the longest detection latency, it can still report 85% of errors within 5K cycles. Since architectural recovery mechanisms generally perform the checkpoint at a much lower frequency, we believe PAS has minimal effect on this method. To conclude this work, PAS combines two different checking methods to detect control flow errors. For intra-interval control flows, it accumulates a unique control flow path and defers the checking until the control flow exits the interval. However, it still validates every control flow that across two different intervals to ensure the correctness. Although PAS reduces the checking frequency to the interval granularity, it can still keep the same level of fault coverage as previously proposed conservative checking methods. PAS reduced the performance overhead from 64.7% of the CFCSS technique down to 15.5%, and it can further extend to protect inter-procedural control flow transfers at the cost of an additional 3.6% performance penalty. That's all for my today's presentation. Thank you all for listening. If you have any questions, feel free to send me an email.